right, so we will begin the last lecture of supersymmetry. If you haven't already figured this out, I have but barely scratched the surface of this, theory and all of the different consequences associated with it. I did a few introductory things, so those of you who didn't know about it, you got a little bit of introduction to it. Those who already knew, you were able to sleep and, you know, enjoy, and, which from some people I heard was actually necessary, but that's fine. Because there's so many other interesting lectures you have to keep awake for, right? But just for reference, like in our SUSY, I didn't go back and count, but my guess is half of the lectures were in some form supersymmetric. Okay, whereas here we have just a little bit. So, what I want to do today is to sort of discuss or finish up discussing electroweak breaking to get to the point of the little hierarchy problem, and then I want to touch on flavor in supersymmetry. I will only be able to touch on these things. There are a whole number of other topics that I had grand plans to cover, but this is life. What I think I'm going to do, though, is I can already anticipate I'm going to go over. So by some order epsilon that's not so small. So what I'm going to do is when noon comes around, I will stop at what I think will be a stopping point. And then those of you who are done with this, go get lunch, you know, take off. Those of you who want to hear about the topic that I will mention at that point, then are welcome to stay. And I'll spend about maybe 15 minutes on this last topic. Okay, so that's the plan. And let's proceed. So we left off last time with the Higgs potential in the MSSM from the two Higgs doublets, where I have written only the neutral components right here. Okay. The key feature of supersymmetry over and above any other random model is that its quartic coupling here is determined, right? And that's the origin of why the prediction for the Higgs mass at tree level is related to the Z mass, because as you can guess, when you turn these gauge couplings around into what the Z mass is, it corresponds. Okay, up to whatever this, however the expectation values go through here. I'll get to the red stuff later. Okay. So what we want to do then is to take this potential and just analyze a few pieces of it and extract out the relevant equation for what is generally known as the little hierarchy problem. All right. So I already said, I said last time that you could take, you could choose expectation values that are real and positive. This sort of follows from just doing SU2 rotations on the fields. And that's why this is only written in terms of the neutral components. Then you can also, there's phase rotations and so forth, so we can take B to be positive. Let me not belabor that point. But then from there, we can then analyze the potential in terms of searching for a minimum and determining whether electroweak symmetry is broken. So, sorry. You know, the one day I don't put this on airplane mode. Sorry, just give me a second. I had a clock up. Okay. Okay, so we want to search for then the conditions for electroweak symmetry breaking. So the first issue is that if I stare at this potential, you see that there is this interesting term, the quartic term, which is not just a quartic in the Higgs field, but is the square of H naught, HU squared minus HD squared, which means nothing other than if I take the expectation value here equal to that guy, then this entire term vanishes, right? This is known as a D-flat direction in field space. D-flat because this came from the D terms of supersymmetry. So if we are in this potential, if we go along this direction, right, then there is no quartic term to pull the potential up, which means then that there is some condition that the rest of the terms must satisfy such that the potential is itself positive, so it doesn't fall off to infinity at large field values. And so that corresponds to just taking, well, the sum of these terms. So let's just write it out. So it's mu squared plus mhu squared plus mu squared plus mhd squared plus b squared is greater than 0, or, sorry, because I've got a sign there, then, So the choice of sign here is just is one of those choices for b. So then this is actually minus b, but there's 2b because of this plus Hermitian conjugate. So then this is greater than 2b. Okay. So this is the condition then for v greater than 0. So then the second condition, of course, is that it has to have a minimum away from the origin. And one can go and search for that. Now, the easiest thing to do there is to, again, just look at the potential and take derivatives of dv by dh, and look for then what the mass matrix looks like in terms of evaluated at the minimum of the potential. For us, of course, we have both HU and HD, so this is a 2 by 2 matrix. So we can do that. So this looks like in HU and HD space, u squared plus mhu squared, mu squared, mhd squared, and then the diagonal is e. So then, so from this mass matrix, then you can just look for a condition for a negative eigenvalue, and there are sort of a couple of possibilities. You can run through the two different possibilities and determine that the one that's relevant is that the determinant of this matrix is negative, which corresponds to, well, we can just do this, and that works out to mu squared plus mhu squared. Has to be less than b squared. Okay. So for minimum. Away from the origin. So then with these conditions in mind, the potential will then have will have a field direction away from the origin where the where HU and HD in general get expectation values. I actually began to do this last time because I was already sort of thinking, and I was running ahead, if you like. So this is usually called VU. This one is VD. They satisfy the usual sort of conditions, which is that V, let me get it straight now, 174 squared. And let me tell you, the number of times that the difference between 174 and 246 is screwed up a factor of 2 somewhere is more than I can count for many papers, and I think I've even suffered on this one now and then. Anyway, if you want to be kind to referees and other people, you know. Anyway, okay. Hey, what? Yes, but then you'll talk to other individuals who will tell you that it should be 246. Oh, yeah. Well, I'll let you and Adam Martin battle it out. Moving on. You know, sorry, this reminds me, I hate to digress on little stories, but this reminds me of when Veltman used to tell us in grad school, he's like, the issues that are always most passionately debated are those which are completely irrelevant. He was referring to the metric. Okay. Okay. This is normally then written as with, now let me get my stupid sine beta v c beta v, such that tan beta is, if you haven't already seen this in 100 colloquia. All right. The fact that supersymmetry is a 2 Higgs doublet model, of course, means that you're inevitably faced with having the ability to have some expectation value in one or the other doublet. And then, therefore, there's a parameter that tells you something about that. How much goes into one or the other, well, is ultimately determined by this potential and solving for whatever the expectation values are once I put in proper values for mu and mh up and down and b and so forth. Okay. Which is my next thing on this line. Okay. So you can go ahead and solve for these minimization conditions to determine what the expectation values are. I don't think I need to bother with that. I think you guys know how to do that. Let me just write out what then the result of those minimization conditions are. So these are, of course, the dV by dHu and dV by dHd. This is a partial. This is a partial. Probably used to this by now. Okay, so if I do that and I solve, I get two conditions. You take the two conditions, manipulate them, and you end up with 2, 0. And I think did I get all the signs right? Yeah. Now, we didn't have to write this in terms of nz, but because of the fact that the potential already had this g prime squared plus g squared, it's convenient to just reabsorb that in terms of, excuse me, in terms of the V174. So that's the origin of where this thing came from. The rest is just the parameters of the theory. One limit that's interesting, so in the limit of large tan beta, which for now is not obvious why that's such an interesting limit to go into, but let's just imagine we did that. Now when I say large, I don't mean a billion, I mean just large enough compared to 1 that then this thing is small, and then if I go ahead and do this, you see large enough tan beta means then that this guy dominates, so I end up getting 1, and I sum all of these terms up, and you see that that to leading order in tan beta, then the down guys cancel the ups, add together, and I get mz squared is minus 2 mh up squared plus mu squared plus corrections that go like 1 over 10 beta squared. Yep. Wait. I'll tell you. Good. So this is it. At large tan beta also, this thing then sine 2 beta goes to something. small, I believe. Okay, so this goes away. That's corresponding to the B parameter becoming small. So be it. It is what it is. These are otherwise that parameter, along with mh up squared and mh down squared, and mu for that matter, are otherwise undetermined parameters of the theory. Mu being, again, the mass that appeared in the superpotential, so a supersymmetric mass of the theory, the only one in the MSSM, and mh up squared, mh down squared, and B being these parameters that come somehow from supersymmetry breaking. So this thing here tells me then that to get electroweak breaking at the value that we observe in nature, 174, or rewritten in terms of mz, I have to take a soft breaking parameter, mh up squared, and balance it against mu squared in such a way that this is a little bit larger than, but negative compared to mu squared, right? So that this whole thing gives me mz squared back. This is one of the curiosities of supersymmetry, is the fact that I need to sort of tune one thing against another. How much tuning? Well, that then just depends on the values that I can take for the different parameters. Now, a minimal level of tuning can be associated with whatever the superpartners acquired mass from just this mu parameter. And remember that the mu parameter in a supersymmetric theory gave me masses for the scalars over there, right? But also gave me a mass for the fermions, the so-called Higgsinos, the fermionic partners to the Higgs. The Higgsinos include, right? You have both, I don't know what they're normally written as, but so you have both neutral guys as well as charged guys, and there's up and down and plus, minus, blah, blah, blah. So there are fermions that have both electric charges. Anything with electric charge here means then that it could in principle be produced, and would have been produced if we had already seen supersymmetry by now, at least Higgsinos, by just Drell-Yan. Right? So this going through a photon, and then you produce this Higgsino. I don't know how I want to write it, but H plus and H minus. Okay, the fermions associated with this. LEP2 was searched for this and didn't find it. So that's a bound roughly 100 GeV within a percent or two. Okay. So then that tells you then that this parameter has to be larger than roughly 100 GeV. And that's fortunately not tremendously far from this value over here. So as long as you were able to sort of, arrange these two things to be close, life wouldn't seem so bad. Okay. But there's another sort of difficulty with this, because everything that I did at tree level. And of course, there are higher order corrections that come into expressions. And in particular, in this expression, the thing that is of most concern is this soft mass squared, the Higgs mass squared. Yeah? Right. So the question then is, it's not so much it's not a matter of is this tuned, it's a matter of how much it's tuned. Now, as I said, the bound on this 100 GeV. This one, someone probably told you, is 90 whatever it is, 91.2, or I don't know. There's more digits on it. Close enough. Okay. So we've got. So these are not that far off, so it doesn't smell like a huge amount of tuning. On the other hand, if this parameter were 10 to the 10 or GeV or something very large, then I would have to fine-tune this enormously. So first of all, I'm not really in the d-flat direction because that corresponds to taking tan beta of 1. Okay, so that I avoid. Yeah, but here, to be able to go from there to there, all I needed was tan beta of 10. And I did this for only one purpose, just so that I could simplify this expression to that. If you like, you can actually rewrite this expression in terms of parameters of the 2 Higgs doublet model. You can actually write it in terms of ma squared times some quantity, and then basically something like this. So then if you want to think about the extra, so the parameter, because you probably know about this, if you want to think about the issue of the additional Higgses in the 2 Higgs doublet model and just raise them up a little bit, then you rapidly end up into this limit. So you're back to this again. So I actually have not given you any sleight of hand here in that sense. There are many other sleights of hands I've done over the past 3 lectures. This is not one of them. Okay. Anyway. Okay. So this is the issue then, is trying to match these things up. So this mh up squared is itself a scalar mass squared, which by definition of supersymmetry has no quadratic divergence associated with it, but it does have a log divergence. No one tells you you don't have logs. You get logs. It's that's life. So it's log divergent, and at least it's log divergent in the MSSM, and the RGE for that is this, where I've neglected some smaller terms. Okay, so these are the largest terms, those proportional to the top Yukawa squared, and the Electroweak G2 squared. Okay. So this log divergence associated with these masses, it's not clear what I'm exactly supposed to do with this, but the whole point of using an RGE in the first place was because I had presumably some scale where I broke supersymmetry, it gave me masses, and then that happens at some higher scale, and as we know with separation of scales, we have an effective theory there, and then we just run parameters using RGE, which resums the logs, the large logs that would have otherwise been there if we had had this high ratio of scales. If you do this at leading log, meaning you just take this RGE and solve it, okay, with ignoring some bits, and I've ignored this bit in this solution, then, well, you'll recognize all of these terms showing up here. But anyway, you get this result, where I have to explain what are all of the moving parts in this. So the moving parts include Q3 and U3 squared. So these are the soft braking parameters for the left-handed stops and bottoms and of the 3rd generation, and the right-handed guy here. Let me come back AT, but let me tell you what that is in a second. Proportional to YT squared, and a log. And the log is sort of by definition going up to the cutoff of lambda, whatever that may be. We don't know what that is. That has to be at least as large as the SUSY breaking scale. Okay. So now, if you look at sort of the size of these terms, it's naively suppressed by a loop factor here. But on the other hand, you have otherwise parameters that are transform under color. And we already know from, for example, LHC that we have not observed particles under color, like stops, with various assumptions about spectra, blah, 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 up to, hundreds of GeV, 500 or so, depending on, which model you work with and so forth. So this is already sort of curious. And then, of course, you've got the log, and then you have to figure out how big this thing is. So there's this interplay then between how do I arrange for these to match up to give me the Electroweak breaking scale, and yet I have this intrinsic sensitivity associated with these particles. Models in the literature will usually then say that the resolution to trying to minimize the tuning would dictate that these parameters shouldn't be particularly large, at least in leading log. Okay. So stop masses and presumably this AT parameter. Let me make just one quick comment on AT. I seem to have already erased it. There we go. Okay. What I said, I may have said AT last time, and I don't remember whether I said AT or HT. But there are two. This is one of these wonderful confusions in the, well, anyway. Different people use different things for reasons that I could get into, but the parameter that is associated with the soft breaking scalar trilinear coupling is normally called H in Steve Martin's primer. It is very often, though, instead called AT in virtually many other papers, but it's rescaled as the Yukawa coupling times AT. The origin of this is that if your SUSY breaking is communicated in such a way that it sort of respects the flavor symmetries associated with this YT usually inevitably shows up here. I just made a broad brush statement. I'm not going to get into all the caveats to that. I'll come back to something about A terms, about flavor later. Okay, so we'll come back to that. We haven't got to that yet. Yeah, we haven't got to that. So just bear with me. So for now, all we've done is done minimization conditions to get the electroweak breaking scale itself. We have not yet computed the mass of the excitation about the minima, right? So we haven't done that. So let's do that. How much is related to how big are these parameters? I could give you a number, but I'm not sure if it has meaning. So the problem is, I would have to lay out a few bits to be able to give you a precise definition. But what I can say is that sort of, if you imagine that this stuff is contributing at sort of the, so I just did this in a paper. This is why I'm trying to reconstruct it. But if you imagine that you take this and see, again, I have to be precise about what I mean by it. But let me say it as I think you end up with roughly 10% tuning if the stops are roughly 450 GeV squared each. Now, I can tell you where that number came from if you want offline. Let me not get into it now. Okay. All right. So, but I want to get to this issue of the Higgs mass because that is then the additional piece to this puzzle, right? So the Higgs mass is, again, something that we can just plug into the potential once we have our expectation values and then compute. So by that, what I mean is that you take H0 and U and D, and this is written as VU root 2 H0 H0. Oh, I can clearly see I'm doing something that's, there we go, I'll do that. Sorry, right. Sorry, this is, now I know why I'm doing this. Much easier if we actually follow this. And then it's G0 and A0. And this is beta I over root 2. Where And yes, beta and alpha are defined differently. So I expand the neutral components in terms of the expectation values plus their fluctuations. And of course, in the neutral component, there is also one guy we identify as the goldstone for mz. You do this, you can turn the crank and show that mg squared is 0, as it should be. Again, at tree level. Do the same thing for the charged guys. You work out the Higgs masses. So I really only want to concern myself with the lightest Higgs. If you care about the heavier Higgses, easy enough to find them. The lightest Higgs is some expression which is easiest, again, written in a particular way. The particular limit that I want to take is, again, sort of large tan beta. The extra doublet is somewhat heavy, so decoupled, as they say. You don't have to go very far before you get into this limit. And once you do, you find mh squared is mz squared cos 2 beta squared at tree level. So this was sort of from the very beginning, one of the fundamental issues, right, with supersymmetry. Naively, if you didn't know anything else, you would say, right, Higgs mass is less than z, which is now dead. Okay. Cos 2 beta, of course, is secretly coming from the fact that when I rewrite HU and HD, when I rewrite these things in terms of the expectation values, and then instead of writing it in terms of VU and VD, I write it in terms of V and then beta and manipulate, bam. This is what you get. So, someone asked large tan beta. Why go to large tan beta? Well, let's see what happens when you go to not large tan beta. Specifically, obviously, when tan beta is 1, which is that these expectation values are the same, then you are exactly along this d-flat direction at tree level. So then this whole term vanishes. And so then there's no quartic coupling. No quartic means no Higgs mass. Tan beta goes to 1, Higgs mass vanishes. So the reason for going to large tan beta is this at least is getting closer to, MZ is closer to experiment than 0. Okay. But not close enough, right? Well, decades ago, people realized that this is not the only contribution to the Higgs mass. There are also additional contributions. And if I want to write them sort of, diagrammatically, what we have is, well, first of all, what do I really want to compute here? I'm not so much computing a Higgs mass, I am, but what I really want to compute is what are the corrections to this quartic coupling. Okay. So the quartic coupling is right, this interaction, which is up to some definition of a 2. It's g squared plus g prime squared. And then either a 1/4 or a 1/8, depending on who's defining it. Okay. So corrections to this can include things like a top loop. It can include stop loops. Okay. So Higgs is on the external, right? Stops in the middle. The theory that we constructed last time, where I included just the stops, I did that for a reason again, because the corrections that we're most interested in then are those that would come from these diagrams. Now, all right. And there's more than just this, by the way. Of course, there's other diagrams. Obviously, I'm not going to compute it here now. If I do, then I end up wasting the rest of the lecture, and I still get the 2 wrong. Okay. So let's not do that. But I will tell you what form it has to take. So one thing is clear, which is that we had no quartic couplings in the Higgs potential outside of something determined by gauge couplings, right? So in a supersymmetric limit, the only quartic that's left is this guy. So that means that whatever form of these diagrams has to take, and they certainly sort of naively look log divergent, we know that the sum of all of this stuff has to end up being something like the log of m stop squared divided by m top squared. Now, how you do that? Well, you compute this, you compute that, blah, blah, blah. But the reason that it had to be, if you like, finite with respect to the stop mass is, again, precisely because we're determining this, what the size of this quartic coupling would be from these diagrams. Okay, so this is already one piece of this calculation. The rest of it just then, well, we can sort of read off what the bits have to be. So you can see that I've got either in this diagram or in this guy, I will have a yt to the fourth. Here I'm getting it because I've got a Higgs interacting with the top. Here I've got a Higgs, stop, snop. And this is coming from one of these F terms where I have a yt times two scalars, quantity squared, mod squared, so I get a yt squared. Okay, and here and there. So the whole thing then, am I doing this in terms of the, what am I doing here? One moment. Well, okay, it depends on how I want to do this. So let me do it with respect to the mass. So I've got then, let me pull down the log again. So I've got the log of m stop squared divided by m top squared. I have a loop factor, which is, well, let's just write it, 16 pi squared. I have a yt to the fourth. And then, since I'm extracting out something that is now for this dimension 2 guy, there has to be some scale here. And the thing that's usually done is then that becomes the VEV, which would then make this yt squared mt squared. Okay, when I combine that up, if I go to large tan beta, then I can look at the amount of this guy, this h0, and how that couples to top. And you can convince yourself that that then goes like sine beta. Do I have this straight? Yeah. So it goes like sine beta to the fourth power, where two powers get absorbed into the definition for mt, and then 2 powers remain outside. After that, these are all the things I can do without thinking. And then after that, then I just need to get the 2's and the, well, sorry, there's one more factor that's obvious. I've got color, right? So I've got a color loop, so I've got a factor of 3. And so then the only thing I haven't got right is the 2's. And the correct factor of 2's is 4, I believe. Yeah. Where, for the sake of argument, I took the stops to be equal in mass there. Okay? So this is then the correction to the Higgs mass, and at least at one loop. And this has now been, and you know, this is very simple. We just did this diagram. We can keep on going. You can compute higher orders, and people have done this to many, many loop orders by now. For which, by the way, the higher loop orders are actually important. Some of them subtract, some of them add. You have to run through the whole calculation to get it. In this particular instance, I have not included, shall we say, left-right mixing of the stops. That is what happens when AT is non-trivial, okay? But this at least gives us some handle on how big the corrections would be for this. So then you can go and turn this around and figure out, well, what values of stop masses do I need to get the Higgs mass high enough? And here is the sort of the fundamental conundrum, right? That expression requires us to try to boost the Higgs mass up to 125, our famous LHC value, or whatever it is, 126, through a correction that goes as the log of the stops divided by the top mass squared. However, to get electroweak symmetry breaking here, we have corrections that come into MHU squared, which we saw from this leading log expansion of MHU squared, the RGE, that come in quadratically times a log of the cutoff. So I boost my stop masses up, I can raise the Higgs mass up, and then I increase the amount of tuning quadratically. That is at least with respect to, or maybe I should say this is the modern little hierarchy problem given our observations of the Higgs mass. Before we had observations of it, we only had a bound, but the bound then also led to this sort of constriction. Okay. Now, how bad is it? All right. Let me sketch a plot. I don't know what I touched, but it's wet. Okay, anyway. And I don't think it was me. Just saying. All right. That's it. No wonder. All right. I feel like I've got concrete on my hand now. Okay, so if I'm interested in seeing when does this work, so many people have done this type of computation and they rephrase it in terms of the following. They say, well, we already know the LHC has observed a 125 GeV Higgs boson, so let me demand that I get that value and then reconstruct what stop masses and mixings I need to get such that I got that value to begin with. So that's what they normally do. The value that you need for sort of following this line of argument where you have equal mass stops and no mixing is sitting up here at roughly 10 TeV. And whether it's 10 or 7 or 12 or whatever the exact number is, doesn't really matter. Okay, I mean, it's a large value. So this is one sort of data point. Yeah, meaning large tan beta, meaning that I've maximized this. Yeah. Correct. That's what yeah, exactly. Without mixing. Correct. So then what people do, because there is a third parameter in the game, namely the stop mixing, they put stop mixing down here. And let me not write a variable. Let me just write stop mixing because everyone seems to define it differently. So if I do this, whatever I draw will be right. Okay. And it looks sort of like this. I may not be, okay, let's just do it. And also the contribution from you and blah, blah. Exactly. So that's exactly what I'm sweeping under the rug when I say. So some things I sweep on the rug, some things I don't. Here's one that okay. So with the stop mixing, and again, the issue here is that the parameter I need to get this point, if I remember correctly, it's maximized when the mixing is roughly √6 times sort of the stop mass. And my problem is I never remember whether it's √6 times the stop mass squared or okay. Anyway, I can give you a reference for a plot that will give you every last detail you're interested in if you want to know. So, and this value here, sort of the neighborhood of, I think it's the neighborhood of 700 GeV for the stops, but because I think I've got large mixing, I actually don't have two of them at 700. I've got one of them light and one of them heavy in some sort of strange hierarchy. Okay. Large. Okay, so this is where we seem to end up. And trying to understand how it is that you could get the value that has been observed by experiment, minimize the tuning in sort of this way is one of the sort of problems that we have right now. Let me just round out this discussion, yeah? Okay. So you might think, well, okay, so it's obvious. That's going to minimize my tuning. So I must live, well, here or here. It doesn't, I mean, whichever. And by the way, these are not exactly symmetric. But again, I can give you a plot if you want details. Okay. But so clearly it would seem like, well then, this is sort of dictating the kinds of stop parameters that I need to sort of solve the little hierarchy problem, or at least minimize the amount of tuning in the supersymmetric theory. But the problem with this is that this stop mixing is, of course, then related to having a large stop mixing parameter, AT, from over here. And so now I'm sort of using this notation of this YT-AT. Now, when I say large, I mean large in comparison to the stop masses themselves. So then you have sort of, you are allowing yourself to sort of pull the masses down somewhat, but at the expense of having to raise another parameter. You can ask, again, the obvious question. Well, wait a second. I just went over here and told you that these parameters, if they're very large, I'm ending up having to tune. So now if I make this thing large, am I having to tune? Yes, you are. Just not quite as much. And how much it is, again, depends on exactly where we are in this curve and how big you want to get. But the problem remains of how you generate one of these large ATs, if in fact this is the solution to the problem. Okay. This is all in the MSSM in the sense that this is in a model in which the only tree-level contribution to the quartic is this g squared plus g prime squared. There are variations on a theme where people have attempted to say, well, this was all fine and wonderful to have a g squared plus g prime squared. Perhaps I can add another field to the theory and give it another contribution to the quartic at tree level, and then this goes under the name of the NMSSM. You have enough technology to sort of guess what the field you would add, how you'd write it in the superpotential. You can turn that around into the potential and just extract out what the correction, the tree level correction is to the coupling to the potential, and then do that. This has its own issues and well, yeah. This has its own intrigue, shall we say, and whether this is the best solution, the viable solution, and so forth depends on exactly what questions you're asking and on what scales you want to ask them. And that requires a whole lecture to tell you what I mean by all of that. Okay, now questions. Sorry, what? I think I'm still not understanding the question. Let me rephrase and then see if this is what you were thinking. So we have quadratic sensitivity to MH up squared, yeah, in the sense of whatever the parameters are for the stops. And then we have this log sensitivity to the stop masses here to be able to get the Higgs mass large enough. Now when I say sensitivity, I simply mean that I need to take these parameters or the other ones associated with them large enough such that I can match the experimental value. But once I do that, then I inevitably get this loop correction to MH up squared, and therefore a additional tuning between mu, MH up squared, and these parameters so as to get the electroweak symmetry breaking scale, the value we observe. I mean, it's bad to the extent that that if you don't observe these guys, on the one hand, or if you have an independent need to make them large, then you have a conflict, right, within the model itself. Hence, problem. Okay, that's all I want to say about Electroweak aspects. I've got to this point. If this is one of those situations where you have a number of different routes to go. You could say, well, clearly, because this is a problem, SUSY sucks, so I'm not going to work on it. Right? But that was always one of your options, even before we got into all of this, right? You could say, well, I want to work in the MSSM, and I'm going to try to do something. And then I told you something about AT. You could say, well, the MSSM is probably incomplete. There must be more fields, something else going on. So you tack an N in the front, next to minimal, as it's called, and try to solve the problem that way. Okay. I don't know I don't know if there is a solution that is, quote unquote, solution to this, quote unquote, problem that is the best or the one that should be looked for or whatever. But it is at least interesting to think about classes of theories for which this thing can try to go, meaning that you actually resolve this tension. And I would say that that's sort of an active research area among a bunch of different people now, is trying to look at that. It's a sort of a rapidly closing window given the absence of observations of stops at the LHC. Lance. I'm not the expert on the. You usually have to play many games to make that go. I cannot tell you that it doesn't go, but my impression is that. So of course, what usually happens is if you try to take that light, you have to take the other scalars light, including the charged Higgs, and those other scalars have auxiliary impacts on other observables like beta S gamma. So you have to think that through to determine whether that's going to go. Yeah. Yes. 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 Correct. Yes, yeah. Right. Keep talking. I have to erase. In the second half of my 3 halves of my lecture, I am going to tell you about flavor. So, we all know that, well, Ben no doubt taught you, if you didn't already know, that flavor physics in the Standard Model is governed by CKM, and CKM enters through the weak interaction. Thinking where I want to draw this. So for example, a classic violation of flavor in the Standard Model is KK bar mixing. One contribution to that looks like this. Now this is where I have to get my name this right. S. Okay, these are W's. And the operative thing to extract out of this is that we have 4 powers of CKM elements. And we know in the quark sector that CKM is already small, depending on who I'm mixing in with exactly. But in addition, we have 4 powers of G2, weak interaction. The reason, of course, that everything went into there was because you can do this field redefinition of the quark doublets and singlets, and when you do this, the Yukawas become diagonalized. You end up with fermion masses, and the only remaining place where those rotation matrices ended up were in the interactions of the W with the isospin partners. In supersymmetry, we have now many more particles. We have enlarged the sector to have squarks, and leptons, and so forth. And I've already hinted, well, I've already written down SUSY breaking masses for some of the components here. When I did Electroweak, I only put in components for the third generation left-handed guys and the right-handed guys, the uptime. But obviously, all of them are going to have soft masses. So if I write in general a squark star into the potential, say, okay, so this is these are the SUSY, some SUSY breaking terms to this. Then I have some mass squared for that, MQ, but in general, I have flavor indices hanging off the end of this. And I have that for Q, for U. I also have it for Q, HU, UC, I, J. Now, we can write this in different ways, but I will use H, IJ here. Okay. So these are the mass squareds for these guys. Hermitian matrices. This guy, this mass is whatever it has to be, probably plus Hermitian conjugate to make the Lagrangian Hermitian. So if I do the same flavor rotation that would have taken my quark Q, H, U, U, C, and then I had a Q, H, D, D, C in the potential, plus or minus depending on a sign choice. If you want to follow Steve Martin, I believe it's actually negative. Fine. So if I go ahead and do this rotation, I do the rotation on now not just the fields, but the superfields. So we'll diagonalize the Yukawa matrices. Right? We'll diagonalize those guys. But those same rotations that we did to diagonalize YU and YD now show up here. So more specifically, whatever rotation I did on the quark superfield also goes through with the squark. So I end up with Q now in a mass basis. I don't know how to write that. 1, 2, 3. I don't know how to write this. Mass. MQ squared, mass basis with respect to the fermions. And then I have whatever the rotation matrix was, I don't know, U and then U star or whatever it is, transpose dagger, whatever it is. There, Q, tilde. Okay, so once I've rotated away from this basis, from the flavor basis, and then into the mass basis, I end up with this mess. So only for one particular choice of mq squared would this then just go over to the value to something trivial where it doesn't mix the squarks up. Right? So in general, this thing is a 3×3 matrix with entries, right, that can mix all of these guys up. So if mq squared happened to be generated by SUSY breaking in some miraculous way diagonal in the flavor basis, that is to say that if mq squared, so if were in the flavor basis equal to just, well, let's even be more explicit. Okay, times some constant. So this is an abuse of notation, but I think you get the idea, right? So if this is the basis, well then, of course, this will go through, and whatever basis I had for SUSY breaking before will then pass over after I do the flavor rotations. But in general, if this has flavor structure to it, then that will show up in terms of flavor structure with respect to the squarks. Let's look at what this might mean for our friend KK bar mixing. Okay. So so if we extract out the down type squarks from here, and we also have, well, we have an mu squared, and then there's an md squared ij di conjugate dj star. Okay. So if I extract out the down type guys from here and from there, I would end up with a mass matrix that looks like this. So I have a d left, s left, b left. All of these are coming from, right, the q's, quark doublets. And then let me have this hitting d left star, s left star, b left star. But we also have these types of, we also have these types of terms which are then connecting the left-handed squark with the right-handed squark. Okay. And so they go through as now d right, and now I'm worried about my stars, but let's run with this for a second. Sorry, I just want to look at my stars. Oh, I think I am happy. Really? Am I happy? I think I'm happy. Yeah, okay. So then we have D right, star, S right, star, and six by six mixing, where now up here in these three components is mq squared, right, ij. Down here is md squared, ij. And then in these entries includes the h terms, or the trilinear mixings. Okay, so that ends up in here, as well as this mu times some vev times some Yukawa in the diagonal entries. Right? That's what we found last time for the stops. So we know that that's one piece that shows up here, and then in addition there's the h, ij, and one of them is starred. So that's what the squark mixing should look like in general. And this is just for the down type squarks. Of course, the up type have the same thing. Sleptons have their own thing, and so forth. Right. So we have these wonderful matrices. So what do they do? You mean, sorry, in the diagonals here, or in the which diagonals? Yeah. Oh, sure. Good. Yeah. Okay. No, you're absolutely right. You're absolutely right. Yeah. Fortunately for the down-type squarks, they're all small compared with the typical scale of SUSY breaking that we're probably going to have. But you're absolutely right that it's not small for the stops, which is, of course, one thing we found last time. Okay. So what do all of these entries do? Well, we see up here our friend KK bar mixing, and we can now imagine diagrams that would go through in which the flavor mixing doesn't have to go through the CKM elements, or even for that matter, through the weak interaction. And if you haven't already seen these sort of diagrams, here's one of them. So I have the same external particles, but internal I have now gone over to the superpartner to the gluino. So this now has a strength of no longer 4 powers of G2, but it's now 4 powers of G3, the strong interaction. And I'm connecting, say, a down quark to a strange quark, so down to strange. So then this goes through a down to strange, right, like that, with, in a mass insertion basis, a mixing between D and S that is coming precisely from elements like, I need new chalk, elements like this guy, that guy, and so forth. Okay, and the others. And there's this and that, and okay, you know, you get the idea. Right? So I can do that on this side and do it on, same on the other side. Okay. Okay. So this is the size of these contributions. You can go ahead and compute them, and let's see how big they actually are. Now, KK bar mixing involves, in terms of so KK bar mixing is a small thing. So being good effective field theorists like we are, what do? We have our high energy theory, we integrate out the heavy degrees of freedom, we match that to an effective theory for which we then go down to the scales of where KK bar mixing occurs. You know, RG evolution, Wilson coefficients, the whole game. And from that, there are several kinds of operators that can that enter for the weak guy and, for that matter, for SUSY. Well, I should say that the SUSY contributions then contribute to the different operators corresponding to KK bar mixing. And there's several different operators. The size of the contribution you get, though, you can sort of estimate, again, by just sort of staring at this diagram for a bit. So in the limit that the gluino is not far heavier than the squarks, then you can actually work out the contribution, the typical contributions to these, to the operators, to the operator coefficients. So these CIs then go as some loop factor. They then have 2 powers of, right, the mass mixing sitting in there. So I have MDS tilde squared, that's one of them. Quantity squared, that's 2 of them. All of this divided by some average squark mass, presumably, squared, if I can imagine a basis in which these elements are not so large that I can, again, do mass insertion without having to actually do the actual rotation and then putting the angles in here. You can do that 2 by 2, it'll all work out in the same way. Okay, so we've got that. Sorry, I need, all right, so 4 powers there. It's to match up with this guy. This operator is dimension 6, so I know that it's suppressed by the largest scale in the problem. The largest scale in the problem is then either the gluino or the squark. Let's treat the squark one first. So we have M tilde squared, where again, as I say, M tilde here. M tilde is some average. And I'm going to take this to be not really small, but okay, just a perturbation. Yeah. So we've got that far. We have G333 all the way around. That's 4 powers. That's alpha S squared. So that pulls away some powers of this. I'm probably back to 4 pi. I'll check my pi's in a moment. Okay, so I've got then 1. And then I just need to multiply by whatever the loop function is. Yeah. This is sort of the characteristic size of this thing. Let me just see what I ended up getting. All right. Okay. Can I give you a real number? I think I can give you a real number. I think I could give you a real number. Let me give you a real number. So this is sort of the size you would expect. Sorry, alpha S absorbed 2 powers of 4 pi. So that's why one of the pi's is gone. So then there's a numerical coefficient there. That was confusing me for a moment. One of the operators is for this guy is C1, which is, well, let me say the operator is D left, gamma mu, S left, D left, bar, gamma mu, S left, and the supersymmetric contribution to C1 is over 216 times, let me write it as like this. Okay. Times a function. Times some function of the squark mass divided by the gluino mass. Okay, so now, so it was easy to see this piece. It was easy to see there were no pi's because they got absorbed. It's easy to see that I've got this contribution, which is basically that. Squark mass, at least that's taking the squarks to be heavier, then I get that. That will tell me something about the size of the loop function. We'll get to that in a second. The only thing that I specify by going from here to here is that because this particular operator is involving the left-handed fermions, it means that then these squarks, as they come in here, they interact with glue. Glue, of course, doesn't change the chirality. So you've got left coming into a left-handed strange, left coming into a left-handed down. So that means that I'm actually hitting this element or that element in this 6x6 mass matrix, and that's denoted by left-left. So by left-left, it simply means I'm taking one left from here and one left from there, and I'm pairing those up. Other operators that contribute to KK bar mixing are not left, 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 left. There's also a right, 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 right. And there's a left, left, right, right. And there's several different variations on that. Okay. They each then have their own, you can go ahead and do this computation for each one of them. So there's C1, C2, 3, 4, 5, whatever, okay, for the different operators. And they have a similar form. They are all going to have the same coefficient here. They all have that. They all have some suppression like this, and they have their own loop function depending on, what they are. Okay. So the logical thing is then, how big are these effects? Okay. So if I'm interested in the left-left contributions, so again, the way this is usually done is we know the size of KK bar mixing. We figure out the error on the size of that KK bar mixing. We say SUSY maximizes the error on the KK bar mixing. And then we set a constraint on the size of these parameters. And the constraint is then going to be related to how big is the mixing delta, and then how big are the squark masses. Right? And the only non-trivial thing to do is to compute f, this function, and then take it for whatever particular values I'm interested in. So the answer is that for squark and gluino, okay, then delta left left, delta right right, obviously down and 1 2, that goes without saying because that's the contributions that are entering here, have to be less than approximately 0.05. There is another contribution to, I don't remember which one of the operators it is off the top of my head, but there is a left left, right right. And if I sort of normalize this in the same way that I've done for these deltas, this has to be less than 10 to the minus 3. Okay. So then you can ask, okay, well, how does all of this stuff scale? And you can see that the contributions to these operators are scaling as delta quantity squared divided by the squark mass squared. So to be able to recover, or to imagine that if I had had completely arbitrary left left and right right flavor elements in the SUSY breaking, I would have to raise the squark mass up by a power of the inverse of this number. So this implies the squark mass has to be larger than 500 divided by 10 to the minus 3. And this is GeV. Okay. You can do the same thing for this one, and I think it's 10 TeV. Now, obviously, that assumes that I was able to take these things up to actually sort of, 1, a value that's large. You could say, well, maybe it's not 1, maybe it's Kabibo. Well, Kabibo, this is then, 10 to the minus 1 or 10 to the minus 2. I'm still up at 50 TeV, okay, or some value like that. So huge values, right? Values so large that you would never observe these squarks in any collider, now either planned, now running, planned, or even conceived of. Okay. So this is sort of the power of flavor physics and how it impacts supersymmetry. This is the supersymmetric flavor problem in the guise of KK bar mixing. KK bar mixing is but one observable. There's also BB bar mixing. There's mu to E gamma, lepton flavor violation, mu to E conversion. There are then other quantities that are not necessarily flavor violating, but they're chirality violating, like left-right, like in EDMs, electric dipole moments. And they all tend to push these scales to values that are considerably larger than what would normally be probed by the LHC. This has been known for a long time, right? I mean, KK bar has been, I don't remember when it was observed. I fear if I ask Lance, he'll say, are you treating me as an old, you see, exactly, right. So it's been known for a long time. So it doesn't, this has been around for a long time. And as a result of this, right, the assumption people usually used was, well, it has to be. I mean, there's no way. This must be diagonal in the squark masses. That's the only solution, or otherwise the squarks have to be really heavy, right? It's got to be diagonal. So then decades of model building effort have gone in to trying to figure out how SUSY breaking leads to diagonal squark masses, and something analogous for these guys. Okay. Gauge mediation, anomaly mediation, gaugino mediation, blah, 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 blah. Okay, all of the different models. that's, again, its own interesting program, an own interesting set of lectures, but at least now you see why you want to get into all of that. What I'm going to do now is, as promised, it's just a couple of minutes after 12. I am going to, yeah, that's only a couple. I can take care of this if you, like someone. No, so what I'm going to do is not turn the clock back, but I am going to stop for now. Those of you who are interested, I will give you 20 minutes on an alternative solution where the flavor does not necessarily need to be diagonal, and there could be non-trivial flavor violation in the squarks and leptons, and they could be light. If you're interested in that, stick around. If you're not, lunch awaits you. Okay. Thank you. And while people are shuttling out, I'm happy to take questions on any of this or other bits before I start in. Yeah. So what I'm doing is, so I started with this to get this bound. So all I'm doing is I'm saying, well, imagine instead of this value, but if I imagine taking the delta up to be of order 1, then what value of squark mass would have I had to have taken to satisfy the bound? I should have been more precise, but that's what I meant. Yeah. Yeah, so it really just depends then on what, well, so here the only guys that I needed to have light, or that the leading contributions to the Higgs mass are those with the largest Yukawa couplings, namely the stops. So, right, so that's why these guys are small. KK bar mixing, on the other hand, is dominated by the first and second generation mixing. So you could imagine, and this is one proposal, that say the first and second generation masses are themselves large, but the third generation is light. This would somewhat mitigate the flavor problem while at the same time not lead to excessive tuning here. There are various names for this. It goes back to Nelson, Kaplan, Cohen, in the alphabetically ordered, you know. Okay. All right. Other questions? Yeah. That's correct. Yes, though those are then, because they're suppressed by CKM elements, they tend to be then in line, and you don't need to take the masses excessively large to satisfy the constraints. Minimal flavor violating, if you like. The only sparions that broke the flavor symmetry, hopefully you've already heard about that, the only sparions that broke that were the Yukawa matrices. Right. Yes? Good question. I'll let you think about that. It is. It's a good question. How low can you go? Okay. I will not try to take up too much of your time. I will just give you a little bit. I appreciate your willingness to endure hunger while I tell you a little bit about an alternative. But think of it this way. I'm enduring the same thing you are. So we have collective pain, if you like. Okay. Okay. So in 2007, Neil Weiner, Eric Poppets, don't ask me why I'm doing it in this order. Man, can I not spell my collaborator's name? Sorry, I'm not seeing it on the, okay, thank you. And yours truly wrote down an alternative approach to this, which is, like all supersymmetric scenarios, never free of problems. There are other issues you have to think about, but it at least provided an alternative way of thinking about flavor in supersymmetry. And it went under the name of R-symmetry. So, what's an R-symmetry? One thing I didn't discuss until now is that supersymmetry is one of the symmetries that we have among the various fields and components that we have. But there is another symmetry that may or may not be satisfied by all of the parameters of the theory called U1R. So under U1R, the theta coordinates go to, now let me get my signs straight. So theta goes to e to the I alpha, oops, theta, so the daggered obviously so theta squared goes to 2I alpha, and then d squared theta okay, so there's a few trivial relations out. Because R rotates theta, but doesn't, and components like this, but doesn't rotate the scalar field, then obviously it doesn't commute with supersymmetry. Okay, so you can do, that's sort of obvious just from how this rotation would work. When we write, so interactions such as when we had d4 theta, superfield star superfield, or even with an e to the 2 GV or whatever needs to go in between to have the gauge covariant derivatives. So this has a d squared theta bar. So of course this is R charge 0. Hence this is R charge 0, and it's trivial. The non-trivial piece is in the superpotential, where d squared theta W plus conjugate. So then this, in the theory, so d squared theta transforms with respect to, say, minus 2 units of R charge. So to make the Lagrangian invariant, then W transforms with plus 2 units. Okay. In addition to W, there is also the kinetic term for gauge fields, right? And so since this goes as minus 2, this goes as plus 2, you see then that the R charge of W alpha is 1. Now, the leading component in W, which you may remember, is the gaugino. So there's the gaugino and then the rest, the higher order terms. So that tells me then that the gaugino has R charge 1. Now, one thing I didn't sort of mention, I had a gluino in this diagram up there, and I implicitly assumed it had a mass. I didn't tell you where its mass came from, but the assumption is that there is a Majorana gaugino mass for the gluino, for the wino, and for the bino. And this is the standard thing. A Majorana mass in a Lagrangian right? Looks like lambda lambda m lambda plus, right, plus the daggered piece in two-component notation. So then this has R charge 2, which then tells you that a gaugino mass, m lambda, okay, has R charge minus 2. Or in other words, man, you can't read that, can you? Or in other words, gaugino masses, Majorana gaugino masses violate the R-symmetry. Or put differently, you have to violate the R-symmetry such that you can generate gaugino masses. A different way of phrasing it depending on which persuasion you happen to be when you think about these things. This is, however, well, okay. Now, this largest contribution that I have now erased, conveniently, for KK bar mixing, I think I got to use the board. So this diagram here, we don't need that anymore. We don't need that. We don't need standard model. Okay. All right. So this contribution, in the limit that the gluino mass is larger than the squark masses, again, if you go ahead and compute the coefficient for this operator, this has to go like 1 over the gluino mass squared. Now, it's actually not immediately obvious that it goes like this, gluino mass squared, but where that's coming about is because I have quarks coming in, quark, anti-quark, and I go through diagrams that involve a chirality flip on the gluino line, which is the statement that I'm putting in here, a Majorana mass for the gluino, or in effective field theory language, I'm shrinking this to a point, and I have a dimension 5 operator that has quark, quark, squark, squark coming out of it, suppressed by 1 over m gluino. So then I have that, and I have that here, 2 of them, 2 powers. Bam, done. Okay. Now, what would, well, okay. This type of contribution to KK bar, this contribution that involves this chirality flip, is the largest piece in all of these operators. That would take me your lunchtime to explain. So let me not do that. That's technical. But that's not. But it's not surprising that this would be the largest thing, but it is. Okay. So seemingly then, this Majorana mass, this R violation that is actually sitting right here, is directly related to this coefficient that's sitting there, okay, in the KK bar mixing. What would happen if gluinos didn't have R violation? If there was no R violation, then all of these crosses wouldn't be there. There are some other diagrams, but entire classes of diagrams go away, and the ones that remain are sort of suppressed by additional powers of the gluino. How many additional powers? That we can compute, because now if it's no longer putting a chirality flip in the middle of the diagram, and I integrate out a gluino, I'm going to get something like the characteristic momenta in the loop. Right, so here's the comparison. So Majorana, oh, this chalk sucks. Sorry. Okay, so for Majorana, we have, right, dimension 5. If we don't have R violation, so no R violation, then when I take this gluino and I shrink it, I'm going to get something that is something like the characteristic momentum in the diagram divided by the gluino mass squared. So this becomes, so in position space it becomes a derivative, and in momentum space it's just this. Now, there's an obvious problem, right? one sec. There's an obvious problem, which is, well, this came about because I had a gluino mass. If I don't have R violation, where am I getting a gluino mass from? But if somehow I was able to come up with a mass for the gluino that didn't violate R, then you can see that this would get further suppressed, which then means this diagram down here no longer goes like as it's shown, but it actually goes like m squark squared divided by m gluino to the fourth power. Why this high power? Because now each piece where I shrink this down, right, goes over into this diagram, and the momentum, the characteristic momentum for this becomes the squark mass. Again, something that's non-trivial. I could explain that offline. Okay. But that's how it goes. So the obvious issue is, how do you get a non-R violating gaugino mass? And I'll take the question. All right, how do you get a non-R violating gluino mass? Well, the simplest thing would be in a Lagrangian, I have not a Majorana mass, but some Dirac mass that pairs up the gluino with some other fermion. This fermion now is in the adjoint representation of the gauge group. So I have to extend the supersymmetric standard model to include fields in the adjoint representation of the gauge group. We know that this thing has R charge plus 1, so to make this mass R invariant, this has to have R charge minus 1. This is just the fermion. It has to be enlarged to a whole superfield. The superfield then looks like, well, you know what it looks like. For whatever this thing is. So this field is that field. And for this to have R charge minus 1, this has R charge plus 1. So then that tells you then that this whole adjoint superfield has R charge 0. Okay, just by sort of following the logic. Where does this come from? A Dirac mass. Well, there are ways to do it. I'll write it down for the experts, and those of you who don't know what this means, I'm happy to explain offline. But this arises from a diagram that would look like, or from an operator that looks like this. Where this is a spurion for supersymmetry breaking that gets a D term, and this is the messenger scale. This is the superfield strength for each of the gauge groups, and these are the accompanying adjoints. Obviously, for hypercharge, this is just a singlet. Okay. Now, if all of that doesn't have any meaning to you, just stare at this thing at the top. That's good enough. Okay. Yeah. There is a prime there. It's just I don't know how to. Correct. So in this case, W prime alpha is D theta alpha, I think. I just have to get my theta straight, and then I'll be happy. I think I'm happy. Yeah, I'm happy. Say what? This is a well, you can think of it as a field. Yes, it is a field strength in general, but I'm only taking this as a D component that gets an expectation value. So in the analog of, for again, those who know, if I had, say, an S or an X hidden sector field that gets an expectation value that goes like theta squared F. But now I'm just going to do this for the D term. Okay. So the analog of a chiral superfield that gets an F term, here is the thing for a D. This is the operator. When this gets a D term, this is then D over M. There's a theta here. This guy, the lowest component is already lambda. Theta comes out here. That gives me that. Up to over 2. Yeah. What did I say? Did I say plus 1 or minus 1? Right, so then d theta squared is minus 2. So theta is plus. Sorry, so the Lagrangian is going to be invariant whatever I do. Yeah. This guy minus 2? No, because you see I've got minus 1 here and plus 1 there. No, plus 1. Sorry. Yeah. So this is, the other way to see it is that this is plus 1. This is plus 1, sort of by definition of how this thing goes. So then this guy's got to be 0. Yeah, okay. Good. So a Dirac mass. So if you pair this up with an adjoint, then you can actually give a non-R violating mass to the gaugino. And what's the point of that? Well, the point, as you can already see, is that when I integrate out a gluino, I'm no longer getting something suppressed by 1 over m lambda, but instead by something like p slash over m lambda squared, at least with respect to something in a loop. Yeah? Yeah. Now I've... No, because exactly. Good. Yes. It's a real representation, so I don't have to worry. Yeah, exactly. So, yeah, that's not one of the problems we had to deal with. But anyway. All right, so you can then suppress this. And then you can go and recompute the size of the contribution to kk bar and figure out how big it is. This can be done most easily in the limit in which the gluino is heavier and the squarks are light. And you might think, that's kind of weird. Isn't that tuning one thing against another? There's another magical thing that happens when you have no R violation, or more generally, that you have Dirac gaugino masses. Dirac gaugino masses induce finite contributions to the squark masses through loop effects. That is to say that unlike, say, here in this RGE, where there was a log divergent contribution from M2 leading to MH up squared, if I now generalize this to a Dirac case, there would be no term like that for the Dirac-Wino. Analogously, for the squarks, the RGE for the squarks with respect to the gluino. This has to do with the nature of how what squark masses can be written down given only this spurion in the theory. Now, if there are other SUSY breaking spurions, the argument goes out the window, of course. But if you have only this guy, then it follows that you can get a finite contribution to the squark masses. So it is possible to have a hierarchy, which you have a Dirac mass, and you have scalars, and they are separated by roughly 4 pi. Well, okay, whether it's 4 pi or 4 pi over g or whatever it is, you can work it out. But this is sort of the idea. This is interesting because now when you go back to evaluate this diagram, it then becomes natural to take the gluino, 4 pi heavier than the scalars. That 4 pi then comes in here, right, giving us additional suppression of the size of this contribution. So there's a combination of basically a 4 pi squared that sort of feeds into this. There is the ability to take the gluino heavier without necessarily inducing, large squark masses. So that can be done. That suppresses this further. And then the whole set of diagrams that enter here turns out to be just smaller. There are smaller numerical coefficients. And what you can end up being able to do is to have the squark mixing here being almost order 1, sort of 0.3-ish, 0.2, something like that, in terms of the squark mass squared divided, the off diagonal divided by the diagonal. So very close. Certainly Kabibo is fine, okay? And taking like the gluino to be, say, 5 TeV. So then the squarks are like 700, 800 TeV. Okay, so this is a case where you could have huge flavor violation in the squark masses, and yet it doesn't actually enter into the computation. You can go through, this is but one effect of this. You can go through this for all of the other flavor observables. Mu to E gamma, safe. BB bar, totally safe. BDS gamma, totally safe. EDM's dead, no problem. That's completely solved. What else? What else is there? Epsilon K. Oh. All right. epsilon k you suffer a bit. That's the only one where there's a, and that's the imaginary part of doing this contribution here. That's the only one you suffer. But actually, epsilon k you suffer no matter which model beyond the center model you go. And you suffer by an amount that depends on how big the CP violating phase is in these squark mass matrices. Okay. So it's an interesting, different way of going about it. It has other various interesting advantages when you look at just directly collider physics in terms of the production of squarks and so forth. And that's happily something you'll hear about from Nirmo in his student talk. Okay, so I don't have to talk about it. I would be happy to go through them offline. I won't force everyone to suffer that. Yeah. Yes. So the W prime, again, as I said, I took to be a supersymmetry breaking spurion in the analogous thing where I take S or X to be a spurion, where the only component I'm treating is the D or the F term. So I am telling you this is how you parameterize the SUSY breaking, right, from the hidden sector. If you're asking how do I generate the D in particular, then I have to go through a SUSY breaking model to convince you that I've got a D term there and I've got whatever I've got. Yeah. Yeah, and yeah, that's right. Yeah, but this is remember that this thing is like a U1, so I have more freedom for what I can imagine that I could do with it. So. Yeah. Yeah, so you are correct that you have scalars in the adjoint. And your specific question was? Oh, yeah, absolutely. So if they get a VEV, then obviously you break colors. That's not good. You could have already done that, by the way, in the MSSM. If you take large scalar trilinear couplings, that will tend to also break colors. So it's like anything else. But in this case, the scalars, the real component automatically gets a mass that's of order the Dirac. And the imaginary component, there are different operators that can give it a mass. So once you sort of lift them, then you're safe. Positive mass squareds and you're done. Yeah. That, I mean, admittedly, that's a parameter choice. So there's always parameter choices that potentially give you negative mass squareds. You call those the unobserved parameter space. Yeah. Potentially, and so then that depends then on where the SUSY breaking scale actually is. Fortunately, though, if these arguments about the size of these contributions, even if you have a Majorana mass that is sort of loop suppressed compared to the size of the Dirac mass, all of this stuff sort of goes through and it's still suppressed. You're thinking beta S gamma in particular. I believe so, yes. 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 No. Well, not in this sense. That's an issue for how do I break supersymmetry and make sure I communicate it properly to this sector. The issue is not so much in generating a D term, it's a matter of whether I generate a D term and an F term at the same time and the relative size of them and how much one communicates versus the other. But this is a model building question. Yeah. Okay, well, yes, 2 seconds. Right, so there's one other term that I didn't mention, but yeah, so sorry. So everything that I treated here is treating as if I had the U1, the full U1R symmetry in the theory. But you can when you embed this into a supergravity theory, you will break the R-symmetry by adding a cosmological constant. And that's the issue. So it's a matter of then how much of that breaking is there, and that's directly related to anomaly mediation, because that also is leading to R-violating contributions. Yeah, so the way to think of it is that you could imagine that the U1R is not broken to just Z2, which is the usual R parity, but is in fact a Z4 or something larger, and then that leads to this thing. Okay, I've kept you way over time. Lunch is upon us. Thank you. I've enjoyed it a lot. Keep enjoying TASI. It's a great time. And, you know, it's a great field. It's fun. I feel like the other day I was, at least in the question period that I was in here, I might have felt like I caused some of you to become concerned. And don't get me wrong, I'm certainly concerned with supersymmetry, but you shouldn't be concerned with that because, you know, if SUSY, the thing is that if SUSY's wrong, Technica and all these things, then it's your chance, right, to go off and invent the new physics of whatever it may be. So you can discard all of the conventional wisdom and then move forward. And I think that's really exciting. Whereas, you know, when I came up in the field, it was like, supersymmetry, that's what it is. You have to, da. So in that way, you can think of it as you're liberated from all of the old ideas. So I look forward to seeing all the great papers that you guys write from this. Thank you very much.